Hello, welcome back again into my channel. So this channel is dedicated for all engineers to get better knowledge and skill while using CAD, CAE and CAM software. So in this video, I'm going to use FTI FormingSuite. This is example 4 for metal stamping simulation. And the study case is how to create a symmetrical path and stamping and go finally into the costing. So this is this introduction or the summary for this tutorial. In here, I have one part. So I'm going to create the symmetrical part and joining it together using this connecting surface. Then after this, I'm going to create the addendum and investigate the product design quality using thickness report and also the FLD. And then after this, I'm going to go into this blanking and then create the nesting to find the better configuration. And then finally, I'm going to create the operation to find the die cost estimation process and the hours estimation process. In this video, I will demonstrate how to create a stamping simulation for symmetrical part using FTI FormingSuite. Now at the beginning, we're going to click new to create new project. And then as usual, I always change the unit force from Newton become ton force and remove the decimal number. And also, perhaps you want to change the currency. You can select from this drop-down list what the currency you prefer. But for this case, I want to use the default, the US dollar, and then remove the decimal. Click OK. And then next, we will import the geometry. So in here, I'm going to still use the example geometry from Geo. This came with the installation of the software. The location is in C, program files, FTI, Geo. So in here, I'm going to use the channel brace, this one, as an example, and then click open. Now the file is imported. You can see in here, this is the part. So the scenario for this demonstration, I want to create the symmetrical part in here. And then joining it together, and then to create the stamping simulation. Now for the beginning, I'm going to explain a little bit in here. This is the location where the geometry came from. And then in here we have a geometry set 1, set 2 and set 3. So set 1 is the top surface, set 2 is the thickness surface, set 3 is the bottom surface. So if I click this part 1, you can see the imported geometry it came with thickness. Now this thickness we can measure is 1.2 millimeters, and this thickness will be automatically read by FTI FormingSuite. Now for example in here I will use geometry set 1 and then I define the material. Notice in here the thickness is automatically added in here. Next I'm going to change the material. For example I'm going to use SPCE. Okay, go to properties. No need to change in mechanical. FLD also no need to change, but in here we must add the cost in order to get the price calculation at the end of the simulation. Now for example I just assume this $10, the scrap value may be just $4, extra material costs $2, and the consumable is about $1. Okay, click OK, click OK once again. Now the material is added in here. So next, we have 4 holes. We must close the holes first before they create the symmetry. Click this one, fill holes, and then select all. All the 4 holes is highlighted, and then you can click OK. So this is all the holes that fill in. Okay, next we're gonna create the symmetrical for this part. How to do that? We have in here what is called double attach. So double attach is came with 2 options, mirror double attach and advanced double attach. So if you want to create symmetrical part, you can use mirror double attach. Meanwhile, if you want to create non-symmetrical part, for example, in here we have a right hand and in here we have a left hand. we can use this one, advanced double attach. So in this case, we're going to use mirror double attach. Once I click the mirror double attach, you can see in here, this is the original part, and this one on transparent, this is the symmetrical part. Now, in here, we have what is called the window for mirror double attach. So make sure this one is active, this button for positioning. Then we click the edges on the original part in here. Notice now we have a gap about 4.3 millimeters. Now we gonna create an equal gap in here, along in here about 10 millimeters. So what we're gonna do now, we're gonna make this view as good as possible to create that gap. So in here I'm gonna adjust a little bit. Okay, maybe this one is enough. Okay, now this is the rotate button. This is to rotate the symmetrical part, and make sure you have the gap as near as possible to 0. For example, this one we have a near to 0, and then you gradually increase the gap. Okay, or you can type the gap become 10 millimeters. By doing so, you're gonna get along this curve, okay, between these two parts, you have a gap approximately 10 millimeters. Now after this, you must the connecting between these two parts using the bridging function in here. Now how to do that? I click these edges. Notice when I click, also the symmetrical part is highlighted because both are symmetrical. Now using your mouse, using your left button, drag these edges. Okay, you can see in here the edges is highlighted. You can using your left mouse button, you can drag it until end of the straight line. This is the end of straight line. Now if you feel satisfied with the selection, you can click the preview to see the bridging surface. Now this is the bridging surface. If it's okay, then you can accept it. Now this is the result. So now we have symmetrical part that already connected. Now after this, we're going to create a direction vector. So as you can see in here, we have a quite a complex geometry. So I recommend you to select this auto and then select average normal to calculate all the normal direction vector from the surface. Notice in here, the enforce symmetry checkbox is automatically selected, and also this symmetrical plane is shown. Now I want to check, is there any undercut? No, we don't have any undercut in here. Draft angle analysis. Okay, this is the draft angle analysis. And finally, the term condition. Click OK to accept. Now, the direction vector already created is applied into this double attached geometry. You can see in here this direction vector. Now after this, we're going to create the binder for 3D addendum. So we're going to click create. Notice in here also shown again the symmetrical plane. When I click the silhouette, now we have two options in here. Parallel to symmetry plane as shown in here in this graphical view, and also we have this one perpendicular to symmetry plane. Notice in here the enforced symmetry is automatically on, so when we, for example, create the preview like this, it's always symmetrical. Okay, it's also the same when I want to click this one, parallel to symmetry plane. For example, I create the silhouette in here, it will be shown like this. But for this product, I prefer to create in perpendicular symmetry plane. So let's clear the view and then create preview again. So maybe I'm gonna accept this because the shape is very good, and then I click OK. Now also we need to add the gap in here on the below. The thickness is become minus 10 millimeters. Okay, this is the gap. Click OK. So this is the binder surface. Next we're gonna create this one, 3D addendum. We're gonna select the geometry set. The set is double attached in here, and the direction vector is already defined. So this one and this one. Click OK. Next, we're gonna create the path extension curve. We're gonna increase the offset, become 10 millimeters. And you can see in here, we also have the option, and for symmetry, it's already activated. So this curve always symmetry according to this symmetrical plane in here. Now, what we need to do is there any sharp edges, for example, like this, we must remove it by sliding the smoothness slider. Okay, this already removed. And also maybe we can make it more soft in here by change the convexity. Well, it's not much with the result. Okay, I think this one is good. We can accept. Next is we have gonna is the die radius tangent curve. So in here, the draft angle will reduce. Let me add the smoothness. Okay, the convexity also increase. And this one always a symmetry. Okay, but in here we have a short gap in here compared with this one. So we're gonna edit. We're gonna edit using this edit curve. Now edit curve also available the enforce symmetry. We can make this on, and then we try to edit this. You can see in here the view change becoming to top view. Now we're gonna begin with the pick the start point, maybe this one as the start point. Also in here we have the end point, maybe in here. Okay, notice in here we can remove the attention, so it's gonna become a straight line. We try to pull it. Okay, but maybe we can add a little bit, so it's gonna keep the tangency. Okay, so we didn't start and middle is the same, and then we're gonna pull this one. The tension on the start and the end could be add. Okay, I think this one is good. We can accept this. Okay, I think that's good. Next, we're gonna create a die face. So in here, I usually select the adjust ready proportionally because I want to keep the consistency, the punch radius, die radius, and draft angle. So it means there will be no change in punch die radius, and draft angle. It will adjust proportionally based on this radius disconnected surface that's gonna be automatically created by FTI FormingSuite. So okay, let's see the result. Now we have the result in here. Next, we're gonna create the trim lines. This is trim 2D. Okay, now we have the trim lines. We'll cut both parts, the symmetrical part. Next, we're gonna create the boundary trim line. Also in here, the checkbox already active. Let's check again, is there any sharp edges? If no, we can continue. No, no sharp edges. We can click OK. And then finally, create the first form. Okay, so this is the first form. After this, we start the process setup. So in here, we have a tool mesh setting. FTI FormingSuite recommend the maximum element size is 9 millimeters. I'm going to reduce into 4 to capture all the details of the geometry in here. Click OK. Now this is the meshing result. Let's check the mesh, the element distribution. Yeah, looks good. We can continue. Next is to define the punch direction. We will use the already predefined direction vector in here. Okay, this one. And then finally, check again. Is there any undercut? Nope, no undercut. And draft angle. This is the draft angle analysis. And finally, the trim condition. Click OK. Next, define the forming process. Okay, in here we have 3 options. Well, I'm going to usually click the auto. And then we solve the forming. So this is the forming result. In here we have a flat blank, the color green, and the final form, the color gray. At the beginning, we're gonna investigate to see the final product. Check the report, safety zone. So this is the safety zone. If you don't know about this one, or you need to detail information, you can go into help and click the help this one. It will be directly pointed into the safety zone. Okay, you can read the details what is a safety zone. Also in here we have the forming zone. In here, okay, you can see in here there's a tight panel at the end. And then next we have a safety margin. In safety margin from 0 to 1, you need to check the maximum and minimum value. The maximum is close to 1, the minimum is 0.6. Okay, so I think it's not going to be issue. But in order to make sure, we can check the thickness strain. This is thickness strain, maximum minimum. Okay, this is the maximum minimum. The maximum is 9.3%, is near to 10%. So maybe it's gonna possible we have a strong tendency to be wrinkle in here. Meanwhile, as you can see in here, the minimum is -10, is almost a half of this 20%. So it means it's gonna be safe. There will be no crack, but it's gonna be, we have a thinning effect, so the thickness will be reduced in here. Okay, let's check the thickness report. Let's see in here. Yes, they have this one. The thickness is increased from 1.2 become 1.3. We have a strong tendency wrinkle at the end in here, and we have a thinning effect. The thickness is reduced from 1.2 become just only 1 millimeters, but no crack in here. So I think it's safe because in here outside the product boundary itself, so there will be no issue in here. Okay, this is because this is a trim the boundary of the product. Next, we're gonna check also the FLD to ensure. As you can see in here, there is no red dot that represent the element from the simulation, so it means the product is safe from crack. But in here there is small dot 30% a strong winkling tendency. So yes, it's gonna be wrinkle. But let's go back again. As you can see in here, the thickness trend, you can see in here. Maybe the thickness will be better. This is outside the product. After trimming, this is gonna become a scrap, so there's no issue for this. Okay, now after this, we're gonna check the Springback. So click solve. Now this is the Springback report. You can see the magnitude, maximum, minimum. Okay, you also can check the deflection, this one, maximum and the minimum. But in order to get a good visual report, we can use this one, the shape. Click this, and then we must create this alignment point. At least we have 3 points in here. I usually select when we're gonna create hole. For example, this one. Also the point number 2 and point number 3 in the symmetrical plane. And then I click OK. So this is the Springback report. Now, in here, the Springback report, we will compare with the original part. Now, as you can see in here, I think the Springback is not to look so clearly in here. If you found like this, okay, you can use the feature what's called this one, magnify. Let me show you what is magnify. So this is magnify as if you have a magnification level in here. So it will show the tendency, the direction of the Springback itself. So you can see now it's more clear. The tendency is going up. In here also we have tendency is going up. Meanwhile in here is going down. So you can use this magnification in order to see clearly where the Springback direction go. Okay. And then also we're gonna create what is called Springback after trimming. We're gonna copy this and then first rename it as Springback after trimming. Just modify this input. Click this one and also select the outer trim line. You can only select one. Okay, because this is asymmetrical, so you just only need to check one of it. Click OK, and then let's calculate the result. So this is the Springback after trimming. You can see in here the report about the magnitude. Check the maximum, minimum. Check the deflection, maximum, minimum, and then use this one. Create the alignment point. So maybe alignment point, I'm gonna take the flat shape in here and then click OK. And then use this one, show height path, to see the Springback visualization. So in here it's clearly shown. Okay, so this is the result after trimming. Next, we will continue into the flat blank. So this flat blank will be used to create a blank definition. So this is the blank for the symmetrical part. Okay, next we're gonna create the nesting. So this is the nesting. I will use this one, for example, maybe 4 millimeters. Use this also become 4 millimeters. So the point A and point B, we have a gap 4 millimeters each. Then click this one, and maybe we're gonna solve all. Okay, this is the result. We have one up, this one, with efficiency 85%, but utilization 46%. The cost per blank is 17 US dollar. The total cost is also 17. We have a 2 up, slightly higher. This is 188. It's also 88%. Cutoff dice only 84%. So in here we have a 2 up and a mirror have a similar material utilization efficiency. Okay, maybe next we can continue into the strip nesting. So this is the sheet parameter window. In here we have the default width is 1250 millimeters. The length is 2500 millimeters. So let's accept the default value, click OK, and then for this define layout, maybe I'm going to change become 4. This also become 4, so the gap is A and B is 4 millimeters each. Click OK, and then for all of this layout, we can solve all. Okay, this is the result of strip nesting. Okay, this is the one up, the material utilization, this one, the part utilization, the number of blank 18, 1, 2, 3, 4, 5, 6 times 3 is 18. The cost of blank is 19 US dollar. And let's check for the two up. This is material utilization. Part utilization, the number of blank also in here. The cost of blank also the same, 19 US dollar. Mirror also still the same. Cut of dice. Okay, so this is the strip nesting. Since we have almost a similar result, I'm going to choose the one up to create the line die plan. So this is the layout when we create the OP10. So in here we have purchase and offline. So purchase as if we buy from our vendor or supplier, it will be excluded on the price calculation. Meanwhile in here I choose this one offline. So as if we cut our own blank inside the factory, so it will be included in the price calculation. Okay, and then click OK, this one, and then generate the blanking process. So this is the OP10 for the cutting through the blank. Next step is generate part feature. So in here we have just only first form or draw, and then the trim lines. The trim lines in here also include this one to cut the holes. Okay, next is we choose the process setting. We have the transfer and also we have the addendum. I choose the transfer type, and blank need to be processed for each stamping is 2 blank. Click OK. Since I select 2 blank for each stamping process, now it's shown 2 blank in here. I'm gonna align this become horizontal like this, and also you can change this layout based on minimum fit or based on the nesting layout, or maybe in here you can change the manual, so you can like this one rotate. But I prefer we have based on minimum fit like this. Okay, meanwhile because we stamping a 2 part once a time, so in here we have a blank arrangement using separate dies. This is the illustration for separate dies, and we have this S, a separation between blanks is 300 millimeters. The combined dies is 50. The separation and the layout like this one, and also we have what is called combined dies and punch. So this is the illustration. Okay, for this one I prefer to use the separate dies with the separation between blank about 300 millimeters. Okay, let's click OK button in here. The next step is generate the die liner process. In here, FTI will automatically create this one, OP20, OP30, OP40, 50, 60, and 70. Okay, so in here we have only one action in here in OP50. Perhaps we can change it, or we can drag and drop into this OP40. So we're gonna put in here Once we put in here, the OP50 have no process, so we can delete this one. Also the same in OP50, only one process, so I think we can move it into this one, OP30. So in here OP30, OP50 in here become no process. It highlighted in yellow color, so yeah, we will delete the operation. And also in here we have the trimming to trim both. But since we have a Springback, maybe I'm gonna add a little bit between OP40 and OP50. Okay, so when I click the OP50, you can see in here insert operation before, so before OP50. So we're gonna add this one, okay, and then we do what it called restrike in here. Restrike also, and also restrike. So it means in OP50 we restrike all this surface again. Okay, so let's summarize. First we form, and then we trim this, and also create all these holes. Trim, create these holes, and then we do restrike, okay, to remove the Springback, and then finally we trim, become two symmetrical parts. Let's do the validation. Okay, in here we have, let's see in here, all the warning is interference between part features. So actually this is not an issue. We can continue. Okay, now it's clear, and then we can save the process. Next also we have a summary in here. So this is the summary of the process. You can see in here, let me make it show in here. We have OP10 blanking offline, one station. The die load required is 62 ton force in order to create this blank, and also some additional information also in here. We have a die build is made by casting, and also the die size and shed height, oh sorry, minimum stroke, shed height, okay, stroke per minute, and also the operators we need one for this OP. Meanwhile in here we have a summary for OP 20, 30, 40, 50 and 60. Okay, and in here we have a total die load. So this is actually is OP20 plus 30, 40, 50 and 60. And also we have additional information in here. The die build is still the gang dice, the die size, the bed size, minimum stroke, shed height, stroke per minute. Okay, and also press operators required 4% in here, and also part per stroke is 4. Okay, and then we can continue to cost breakdown. So this is OP10 blanking, cost breakdown, a design, machine, build, try out, material, and also total, and the estimation hours also. And in here the process is the summary for all this OP from OP20 to 60. In here we have the summary about the costs and also the estimation hours. And for the additional information, you can also in this one, it set the generate report, so it means you can save it become the Excel, or you can save it become Microsoft Office PowerPoint. So you can try with your own, this one, Office Excel workbook and this PowerPoint. Okay, so that's it, the tutorial for this. I hope it can be useful for you. Thank you for watching.